Bismillahirrahmanirrahim. Good afternoon, everyone. Welcome at the new lecture. Today we'll try to solve this question. I think it will be the easier one. Let's start to solve it. Now we're dealing with silicon element at the room temperature with donor concentration. Has many results. Start from exponential 14, finish with exponential 17. All these results belong to donor concentration at conduction band. Let's assume Na equals 0. Immediately, that's mean we're dealing with N-type because ND result bigger than acceptor concentration at valence band. Now let's start from requirement A. Calculate the position of the Fermi energy level with respect to the conduction band CP here, not CP, E, C. Let me do that. 1 minute. Yes. E, C. Okay. For this donor concentration, let us calculate the position of Fermi energy level, that means EF, with respect to the conduction band EC for this donor concentration. Let's solve it. After that, we will come back to requirement B. Okay, let me delete that. You can go to another statements. Here, like I said before, we're dealing with N-type. Let's focus on dependent on this result because the author told us calculate the position between EF with conduction energy band EC. Because at the N-type, like we know, let me draw that. It's important. I don't know. I can do that from the side. No. Yes. We have 3 lines. Number 1, E, conduction energy band. The Fermi level or intrinsic Fermi level will be at the middle. The last one will be effective valence band. The last one. Here we're dealing with N-type. That means we will working here. N-type, EC, the conduction band here, minus from EV. Like I said before at the last lecture, we will dealing with the upper one, and the upper one here is the conduction band, minus from the another element below, like EF, the Fermi energy level, because that we write EC minus EF, not EF minus conduction band, okay? Equal KT, that means Boltzmann constant, T temperature, ln effective density of conduction band divided on ND, the donor concentration at the conduction band. Here NC is constant at the room temperature, but if the author change the temperature, we must calculate this result again. Okay. In N-type, ND equal N naught, because the N naught here, the concentration electron will be the majority. Let's put some bracket here, because this will be important to us. EC minus EF equal the Boltzmann constant, temperature, ln effective density divided on donor concentration at the conduction band. Silicon, NC, like we know, at the room temperature equal to 0.8 exponential 19. Here KT equal dot 0.0289 electron volt. Now let's please delete all of that. You can go to another statements. Yes. Now we will depend on this relation and this equation here, ND equal exponential 14. Just we will put it here, and NC will be something like constant. KT here will be constant because we will dealing with room temperature, and calculate all of these here. The difference from valence band to the conduction band equal dot 324 electron volt when ND equal exponential 14, and we will do the same thing when ND equal exponential 15. We will be the same calculation, just we reset here the exponential 15 instead of exponential 14, and we will calculate all of these. Here at last, exponential 17, the same situation, the same calculations. Here equal at donor concentration at conduction band equal exponential 17. This bracket will equal dot 145 electron volt. Now let's go to another important requirement. Determine the position of the Fermi energy with respect to the intrinsic Fermi energy. Here intrinsic at the last one, as the last requirement was the conduction band. We must note that you can calculate and write our solutions rightly, okay? Determine the position of the EF with the EFI level for the donor concentration. Let's solve it together. The position of the EF with respect to the EFI intrinsic Fermi level of donor concentration here with many results of ND. We will depend on this equation. This will be important to us. Fermi energy level minus EFI intrinsic Fermi level equal KT ln donor concentration at the conduction band divided on intrinsic Fermi level for silicon at thermal at room temperature, and I, like we know, 1.5 dot exponential 10. Okay, let's draw this. And after that, let me draw this. EC and the last one. Actually, I draw it below, I think. Intrinsic level EFI. Here, the first thing we must note it, we're dealing with P-type or N-type. Here we're dealing with N-type. N-type. That's mean we will dealing with, with EFN. What this mean, EFN? Let me write it at first. Electron Fermi energy level. Like I said before, you can calculate this relation between these. Let me use another rank. You can calculate between these, the result between these two elements, EFN minus EFI. We will start from the upper one. It's be EFN minus the intrinsic Fermi level, because that we will write the relation the equation like that. EFN minus EFI naught, EFI minus electron Fermi energy level. Okay, at last, KT will be something like constant because at room temperature, Ni will be the same. Just we will change this result. This result belongs to ND. At first, we will put exponential 14, after that exponential 15. The last one will be exponential 17, like the Arthur wrote to us. Okay, let me delete all of that. You can go to another statement, to another information. Yes. Here, exponential 15. Here, exponential 16. At the last one, exponential 17. The difference between the extrinsic Fermi level to the electron Fermi energy level equal 1.599 electron volt. Now let's focus on I think this is the important question. We take it today. Here, the same situation, we're dealing with silicon element at room temperature and uniformly doped with boron. Like I said before, boron has 3 electrons at the last shell. That means it will attain to behavior to take 1 electron from another silicon neighbors, to can reach the stability situation and can build his covalent bonds, okay? To a concentration of, that's mean here with boron atoms, this result, that's mean equal acceptor concentration at the valence band because the silicon is doped with boron. And with arsenic, like we said before, like we know, arsenic has 5 electrons at the last shell. That means we'll attain to donor 1 of them, because it wants to reach the stability situation, to can be stable by saying one of them to send one of them to can reach the stability situation and build its wall, or we can say to can build this its equivalent bond. Here 1.5 dot exponential 16, that means this result equal the ND, because arsenic when donor, when sent 1 electron of them, it will take different charge and will belong and attained with the N-type doped. The question is, it is the material N-type or P-type. Calculate, that's mean we must calculate many equations. After that, we can decide, because here the silicon at first doped with boron and has Na acceptor donor at conduction band, at valence band, sorry, and after that doped with arsenic, that mean has Nd donor concentration at the conduction band, because that we must be careful. Calculate the thermal equilibrium concentration of majority and minority carriers. We know majority will be P naught at P type, and N naught will be the minority at P type doped. And the different things when we're dealing with N type, because in N type the N naught will be the majority and P naught will be the minority carrier concentration. Okay. Let's solve the A requirement, and after that we will come back to B. Here, like I said, silicon at room temperature, boron as acceptor atoms, has 3 electrons at the last shell. That's mean B type. We're dealing with B type. And at the same time, arsenic has 5 electrons at the last shell, and arsenic is donor atoms. How we can give the last choice if we're dealing with N-type or P-type? Like we know, and like I said before, we will do something like comparative between Na acceptor concentration at the valence band with the conduction band, with the donor conduction band at the I'm sorry, I'm tired. With EC, that's mean the donor concentration at the valence band, because that we will know which of them we're dealing with. Here, ND, Na bigger than ND, 3 exponential 16 bigger than 1.5 exponential 16. That's mean we're dealing with P-type. And in P-type, we know Na, P naught equal Na holes, and the holes will be the majority in P-type, okay? And N naught, like I said before, will be the concentration electrons, will be the minority. Now let's calculate the thermal equilibrium. Thermal equilibrium has different equation. We must focus on it. Let me write that. Yes. Let me draw that. Here. It's very important to us. At P-type, thermal equilibrium concentration for majority carrier hole, P naught equal Na minus donor concentration at conduction band. Like we know, let me use the sign. We have Na, and like we said before, we note that we're dealing with P-type because Na was bigger than Nd. That means we can find the last result about the thermal equilibrium concentration for majority at P-type. That means P naught. Okay, let me delete all of that to come see another slide. That means the thermal equilibrium concentration of majority carrier equal 1.5 dot exponential 16. Now let's talk about the thermal equilibrium concentration of minority. We calculated the thermal equilibrium concentration of majority by using P naught equal acceptor concentration at the valence band minus donor concentration at the conduction band. Now let's go to try to calculate the minority at thermal equilibrium, and this minority will be N naught because we're dealing with P-type dot. Here, by using the old law, mass law, N naught P naught equal intrinsic carrier concentration square. By that, P naught, we calculated it here. It's 1.5 exponential 16. And let's try to calculate what the result of intrinsic about electron concentration. Equal intrinsic carrier concentration square divided on concentration of hole. We have the result about the twice Ni at silicon at the room temperature equal 1.5 dot exponential 10, and the P naught like we calculated here 1.5 exponential 16. The last result is 1.5 exponential dot. The minority carrier at thermal equilibrium. Please delete all of this and go to another. Let's talk about B requirement. Additional impurity atom. That means we have a new element. are added such that holes are the majority carrier and the thermal equilibrium concentration is P naught. You know, I have simple mistake because here, let me use, this will be appropriate. Yes, let's use that. That's something like prime to note the difference between them because we have too much of P naught. P naught here, prime, that's mean the new hole concentration, okay? We must use this prime to know the difference between them, okay? For holes to the majority boron, atoms must be added because we know the relation between boron has 3 electrons and they tend to take another electron from other silicon neighbors to can reach the satisfied situation and can be stable. The expression of thermal equilibrium concentration of the majority carriers, P naught dash the new electron, the new hole concentration equal like the author give us to us the example 5.exponential16. Here, like I said before, P naught prime equal it is the new hole concentration at thermal equilibrium. Okay, we have Na, we have Nd results. To find the concentration of impurity atoms in p-type is Na prime. Like I said before, Na is the concentration of the acceptor atoms. We can say the new concentration of the acceptor atoms will be more appropriate. Okay, is added in p-type semiconductor. Let's depend on this important equation. P naught dash prime equal Na prime minus Nd. Now, let's use this. P naught prime, we have this result. Nd result, yes, we have it. Na prime, all we need to calculate the result of Na prime. Okay, Na prime equal the new hole concentration minus new Na plus donor concentration on the conduction band. Here, let's us don't forget Na prime. Okay. The last result to the new acceptor concentration of impurity atoms are added is 3.2 exponential 16 to the centimeter to force minus 3. Okay. Let's delete that. And repeat. Keep going. Thermal equilibrium, the relation of the new thermal equilibrium concentration of minority carriers is N, like the mass law, N naught P naught equal intrinsic carrier concentration square. Here at thermal equilibrium, we will put prime on all of them, concentration of holes and concentration of electrons. Like I said before, we have the result of a new hole concentration at thermal equilibrium, because that, and Ni will be the same at silicon at room temperature equal 1.5 dot exponential 10. That means we can find the last result here by here. We have this result. And we have the result of intrinsic carrier concentration at silicon at room temperature, because that N naught new electron concentration equal dot 45 exponential 4 to a centimeter to force -3 for minority at P type. That's it. Thank you about your watching, your patience, your time. Gelecek derste görüşürüz arkadaşlar. Kendinize çok iyi bakın. I will stop the share now and have a good day, all of you.